In Chapter 5, we're going to be studying integration. And we're going to come to know what that means, but what I want to do is give you a little bit of a motivating idea behind what we're doing in this chapter. If you recall at the beginning of the course, when we first started talking about calculus, we said that there were these motivating problems behind calculus. If you recall, one of our motivating problems was the tangent line problem. How do we find the tangent line to a graph at a given point with only one point instead of two? And we solved this by inventing the derivative, so that gave birth to differential calculus. Another motivating problem that we have is the area problem, and we'll solve this with integral calculus. Now, when we talk about the area problem, I want to be specific about what we're talking about. We already know how to find area of things like circles and squares. It's more complicated objects that we want to be able to find the area of. So how do I find the area of like a kidney bean shaped object? Okay. And we'll look at this right away in Chapter 5. We'll start with this in 5.1, and in 5.1 and 5.2, we'll get to this idea of the area problem. But really, what's interesting about Chapter 5 is that we're going to bring these two ideas together and unite them and find that they're both two sides of the same coin. And the thing that will do that for us, that will bring these these concepts together that seem so very different, is the fundamental theorem of calculus, which we'll see in 5.3. And with the fundamental theorem of calculus, that's when we'll bring in the idea of anti-differentiation as something that's going to be important in Chapter 5. Okay, so let's go ahead and look at 5.1. So 5.1, we're going to be looking at approximating area, but before we get to that, what I want to do is look at sigma notation. So let's write out what this stuff is and then talk about it. To give you a motivating idea for what we're talking about here, let's suppose I'm adding up a bunch of numbers. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. If I wanted to have this sum written out, I could write the whole thing out. Maybe I want to condense this down a little bit, though, because it's a little bit unruly to write down so many individual numbers added up. There's a pattern here. So I could condense this down by taking advantage of the pattern that I'm increasing the number by 1 each time. So I could write this as 1 plus 2 plus 3, and then ... and then 10. And I think that if I wrote that, anyone watching this would know what I mean. They would understand, oh, okay, we're going to add up the numbers, counting by ones up to 10. And this gives us a way to shorten things down. But it has two downsides to it. The first is that it's still not very short. It did condense down this 1 through 10 by a lot, and it would condense down something like adding up the numbers from 1 to 100. It would condense that down by an awful lot because it would be just as long as this. But it relies on you identifying the same pattern that I was hoping that you would identify. And spotting patterns is not a really reliable way to communicate ideas. It might be, in this case, that everyone sees the same pattern, and that works fine. But if I had a more complicated thing that I was adding up, then maybe if I take two people, one person would spot one pattern and somebody else would spot a different pattern, or maybe somebody would have difficulty seeing a pattern at all, and then the whole method would break down. So what we want to do is introduce a way to write adding up numbers that doesn't rely on the spotting a pattern idea. And so we introduce sigma notation. So here's what we're going to do. I'm going to write the capital Greek letter sigma. Then I'm going to put a variable underneath, I. And I'm going to say that my I starts at 1 and ends at 10. And the thing that I'm adding up is I. Let me break down the pieces here. This capital Greek letter sigma is just like, close to an S for sum. Then we have a dummy variable. I'll explain what I mean by a dummy variable. That's actually our technical term for it. When we say I equals 1, this 1 is our starting value. And then this 10 is the ending value. And then here's the formula that we're going to follow. So when I look at this one, my formula is just I starts at 1. And what we do is it's sigma for sum. We're adding. And I will keep going up by 1 each time. So the next step, so this is when I is 1. The next step is when I is 2. And since my formula is just I, I'll just get 2. Right? Then when I is 3, I'll have a 3. And that's going to keep adding until I get to 10. Okay, let's look at some examples here. Suppose I had this. The sum from I equals 1 to 4 of 2I plus 3. So what I do is I say, all right, when I is equal to 1, then I follow my formula, and I will get 2 times 1 plus 3. And then plus, when I is 2, I will have, following my formula, 2 times 2 plus 3. And then when I is 3, following my formula, we'll have 2 times 3 plus 3. And then our last step is when I is 4, we'll have 2 times 4 plus 3. And we could add all of this up and get a total, but the total's not really important here. What we're looking at is the notation for writing out a sum, writing out a bunch of things added. Okay. The I doesn't have to start at 1, though. Okay, we could have something like the sum from I equals 3 to 7 of I squared. Right, this would be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. The key thing is that it's always incrementing up by 1 from the start until it gets to the end, and we only want it to be whole numbers. Another common thing that we're going to run into when we're writing out sigma notation, one of the things that it's useful for is writing out abstract things. For example, I could write the sum from 1 to n of a sub I. Now, this one is a little bit different because I am starting at 1. That's a very concrete number, but my ending value, I don't know. It's an unknown here, right? So I've written an n, but I don't know what n is. Also, my formula doesn't seem to make sense because I don't have some formula of I, some function of i's. This is just a with a subscript of I. Okay, so if I write out what this looks like, when I start with I as 1, this will be a1, plus when I is 2, I'll get a2, plus when I is 3, I'll get a3, and it'll keep going up, and I don't know how many terms it takes to get there until I get to an. Right. The idea behind this is that it allows us to write an abstract idea. For example, let's suppose I want to write a formula for a polynomial of degree n. So what I could do is I could say that this is the sum from not starting at 1, but starting at 0 and going up to n of a sub I x to the I. If I were to write out what my terms look like here, when I is 0, I'll have a0 x to the 0. And x to the 0 is just 1. We'll just have a0. We might run into a problem if x is also 0, because then I'll have 0 to the 0, and that's undefined, but we'll worry about that later. When I is 1, we'll have a1 x to the 1 power, plus when I is 2, I have a2x squared, and this will keep going up until I have an x to the n. So what I have here is a very compact way of writing out a formula for any generic polynomial of degree n, where I don't have to specify what n is, and I don't have to specify the coefficients. It's left as vague. Okay, now let's look at some properties of sigma notation. The thing to keep in mind when we go through these properties is that sigma notation is just shorthand for writing a sum. So we're just adding. All of our properties of sigma notation are going to be things that you already know. They're just properties of addition that we're bringing over to the notation and looking at what they look like. So let's start with the sum from I equals 1 to n of the number 1. If I add up 1 over and over again, 1 plus 1 plus 1 n times, that's basically what counting is. So if I add up the number 1 n times, I just get n. If I, instead of adding up the number 1, if I add up some constant, take a constant and add it over and over again, right? So for example, if I take 3 plus 3 plus 3 plus 3 and I add it up 10 times, If I add up 3 10 times, I get 30, right? I already know that. So how did I get that? Well, I take my constant and I say, well, how many times did you add it? We added it n times. So then we just multiply, right? That's why we call multiplication times. So this is just c times n. Okay, now let's look at another property of addition. Suppose I have a sum, and there's a constant multiple inside my sum. If every single term is being multiplied by a constant, I can factor that constant out. So to explain how this works, right, if I have c times a1 plus c times a2 plus c times a3, I can factor the c out. Right, so we have c times that sum. So constant multiples factor out of a sum. So they factor out of our sigma notation. Another thing that we can do, let's suppose I had something like a1 plus b1 plus a2 plus b2 plus a3 plus b3. I could reorder that and instead say, let's add up all of the a's first and then add up all of the b's. So when I'm adding, there doesn't have to be any special grouping, but I can think of these as being a1 plus b1, and then add that to a2 plus b2, and then add that to a3 plus b3. And I can reorder it so that I'm adding up all the a's first, and then adding up all the b's, and then combining those together. So we can rearrange the order of addition all we want. Right? What does that look like in sigma notation? If I have the sum of ai plus bi, I can break that up into the sum of the ai's plus the sum of the bi's. I want to make a special note here. This only works for finite sums. It does not work for infinite sums. All right, now, why did I bring this up? We haven't talked about infinite sums. We're not about to talk about infinite sums. The reason I bring this up, though, is because in Calculus 2, when you start sigma notation, the first thing you're going to be doing is looking at infinite sums. And all of our properties of finite sums work for infinite sums except for this one. And if you make a mistake with this one, it leads to wrong answers. So I just want to point this out ahead of time so that you've seen it once now. All right. And then let's look at one more property. This one, I'm not going to write out a little example here. Well, maybe I will, but this one isn't really something that we think about doing with addition. It's really special to sigma notation. So let's suppose I have the sum from 1 to n of a sub I. And again, I'm going to write out an example, maybe just adding up 5 terms. Suppose we have a1 through a5. And let's suppose that for whatever reason, I want to group the a1 through a3s as one group of stuff, and then a4 and a5 as another group of stuff. Well, I could write this as a sum from 1 to 3 plus the sum from 4 to 5. So what does that look like here? I could take my sum from 1 to n and break it up. So I could pick somewhere in between. Maybe we'll use little m as our breaking point. And then we have a second sum where I pick up where the first one left off. But I don't pick up at the same spot. I pick up at the next number over, right? So if the first sum goes from 1 to 3, the second one doesn't start at 3, it starts at 4, one higher than where I left off. So what we're going to do is if we start from 1 to m, the next one is going to start at, not 1, it's going to start at m plus 1 and go up to n. So this property, I think, is maybe the most confusing to look at, but all we're doing is saying if I want to add up the numbers, a1 through a5, I can add up a1 through a3 as one sum, a4 to a5 as another sum, and treat those as two different sums. Let's look at some special summation formulas. Okay, we technically already had one summation formula, so I'm gonna write down the first one that we had. If I sum up from 1 to n of a constant c, I get c times n. All right, and we explain that away that's just when I add a number over and over again, that repeated addition is just what multiplication is. So that's why we get the times there. All right, so let's look at the next one that I want to look at. Suppose I want to take a sum from 1 to n of I. So this is just adding up the first few integers, right? The first n integers, 1 plus 2 plus 3 plus 4 up to n. And there's a neat little story behind this one that I like. So Carl Friedrich Gauss was a German mathematician that is one of the greatest mathematicians, if not the greatest mathematician of all time. But there's a story about when he was in school. Suppose you have this teacher, right? And so this is just a story. Nobody really knows if it's true, but it's the story that goes. You have a teacher who every once in a while wants to get a little bit of a break. And if the teacher wants a break, they have this problem they can assign, right? Say, have all the students add up the numbers from 1 to 1,000. Get out your chalk and slate, start adding. And that should kill some time, right? That should buy the teacher maybe half an hour to do whatever, decompress, go out and have a smoke, whatever an 18th century teacher needs to do. And little Gauss comes up after about 2 minutes with the answer. And not only has the answer, but has how he figured it out in 2 minutes. And, if I had you add up the first 1,000 numbers, and I even gave you a calculator to keep track instead of just chalk and slate, I don't think you could do it in 2 minutes, right? Even if you're really quick on your thumbs. So, how did a little 8-year-old kid do this? Well, what he did is he noticed a pattern. So let's see if we can recreate his steps. So I want to add up the numbers. 1 plus 2 plus 3. And I'll put the last few on there. We're adding up to 1,000. The difficulty here is that the numbers are all different. If I take, say, 3 and I add it up 10 times, you say, oh yeah, that's 30. It's because I'm adding the same number over again. We can do that really fast using multiplication. These numbers are all different, and so multiplication doesn't help us. And so what Gauss thought of was, well, let's see if we can rearrange things so that I do have the same number over and over again. So what he noticed was, if I take the first number and the last number, they add up to 1,001. And if I take the second number and the second to last number and I add them together, I also get 1,001. And then we take the third number and the third to last. And every time we create a pair like this, they add up to 1,001. So I have this number 1,001 repeated, and then we just have to figure out how many pairs we have. Well, if it's 1,000 numbers and I'm pairing them all off, there are 500 pairs. So it's just 1,001 times 500, and that's not a very difficult multiplication to do. All right, so we get 500,500. What we want to do for our class, though, is say, well, that gives us a summation formula. If I'm adding up the numbers from 1 to n, I can do this pairing off thing. They're going to add up to 1 more than n. So I'll have like n plus 1, and then the number of pairs that I get is going to be half of what n is. Okay, now the way that we normally write this formula is going to be n times n plus 1 over 2. But it's the same formula, and that's where it comes from. Now, I didn't give you a really good proof here because if n was odd, then they don't all pair up. There's one left over. But we end up with the same formula, and I don't think that it's worthwhile to go through the algebra to show things like that. Okay, especially since the next two formulas I'm going to give you no justification for because they don't have a neat story, and they don't have like a neat pairing technique that we can do. They just have a lot of thick, messy algebra. So we'll just write down the formula. If I add up I squared, our formula is n plus 1, 2n plus 1 all over 6. And if I add up I cubed, we get n times n plus 1 over 2, and that whole thing is then squared. We're going to come back and reference these. These are not formulas that you should spend any effort or time memorizing. They're not going to be so useful that it's going to be a helpful thing to have memorized. So when we're doing differentiation and we remember the derivative of the trig functions, that's helpful because the trig functions come up a lot and we do derivatives a lot. So that's something that you'll see a lot. And even things like the inverse trig functions is helpful because not only do they sometimes come up, but it's also helpful for anti-differentiation. These formulas, though, are only something that you should ever just reference.